Hello, everybody. Now it's getting a little bit old school. The title of my talk today is Fractal Damage in Laminated Glass and Stochastic Fracture Simulation of Glass and Transparent Polymers. My name is Stefan Kolling, and here are the co-authors, Marian here, and also some guys of my group. So, what is fractal damage? That is the first thing that we should discuss. So, the basis for fractal damage is given in already the 50s by Benoit Mandelbrot, which was a Polish-French American mathematician, and he introduced the term fractal first in 1975. What for a pointer. Here, perfectly. Okay. So this is the definition of fractal structure. We see. So, just a moment, please. No. What we can see here is a fractal geometry, and then if we enclose it, then the same geometry is reproduced. So over and over again for all times. This is the definition of fractal geometries. And here's the famous picture done by or simulated by Benoit Mandelbrot, which is the Mandelbrot setting in a continuously colored environment. And another case is this a snowflake, where if we enclose here the picture again and again, we see always the same structure. So in laminated glass, also fracture occurs, and because of the some damage within the glass, and here we consider now a laminated glass. A laminated glass is a windscreen, for example, two panes of glass and a polymeric interlayer in between, which is usually PVB, say polyvinyl butyl. Here is the setup. Oh, that was the wrong button. As you can see here, we have the glass, the upper pane of the glass, the lower pane of the glass, and the PVB in between. This is the laminated glass setup. So here you can see in a car. This is a car of a member of my group, and it was funny to see that we found here also this fractal damage. And also in the windscreen in the area there we can see such fractal structures. So these are the motivation to deal with it. Another one is in ceramics. So you can also see this fractal damage in ceramics. Sorry. So and another one. This is in the surface, and at this boundary here, also some fractal damage can occur. So how to simulate that? So there are some possibilities, and one of this is the percolation theory. So this is originally developed for vulcanization by Paul Fleury, a Nobel Prize winner in chemistry. And the idea is that we go to the lattice area, and here we have L times L lattice, which describes an O1 phase transition. We see some blue points, some red points, and sometimes some clusters occur like here. So at least two red points close to each other, or more than two. This is what we call the cluster. So, and cluster form if the probability exceeds a critical value. So if it is if the probability is larger than the critical value, then we have another effect. We have an infinite cluster. So if diffusion occurs, as you can see in the lower part now, then all the red points are connected to each other, and we leave the lattice at the upper point. But if we have periodical boundary conditions, then we have an infinite cluster. And this occurs if the probability is larger than the critical one. So this is the formation of an infinite cluster. And we can sum up, there is a critical value PC, which depends on the grid type, from which an infinite cluster can be formed. So here an example for percolation, 1001 times 1001 grid with periodical boundary conditions and a critical probability of roughly 0.59. And this is given here, the number of clusters in dependence of the probability, and roughly at 0.6 something happens. And this is the critical probability, PC. So the time to form an infinite cluster increases with the probability P. So fractal geometries depends on the probability P. Usually is that a fractal number. So some examples. If the probability is chosen as 0.586, you see this fractal geometry. If we have exactly P, the percolation point, then this fracture pattern occurs, and finally we are higher than the critical one, So we have an infinite cluster, but only if we consider periodical boundary conditions. Then we have here a cluster to above, and it goes here and in this upper area to an infinite cluster. So here an example. So this is acid corrosion through a container wall. You can see here in the upper part the wall. And the question is, can acid travel through the wall or not? So here a very simple model for that, for this phase transition, 100 times 100 grid. And we are here on the left-hand side under the, or lower than the critical percolation point. Oh, sorry. Oh. Sorry. Can't find the mouse pointer here. But so this is a movie. Hi, great. Here this.
It's not working. The video is missing. Yes, the video is missing. It's not in the cover. So it will not work. So you have to do it without the video.
Okay, that's a pity. But well, if we could say it, what see it, can detect that of the left-hand side, the cluster or the acid it does not eat through the entire wall, and on the right-hand side, it eats through the entire wall if the probability is larger than the critical one. So, sorry for that. So, the background of this simulation is DLA, which has been formulated by Ernst Ising in, say, roughly the 70s. So again, an L times L lattice, which can also be in finite element mesh, with a nucleus in at any grid point, and we have a starting point so that we can now do a random walk, and then two things can happen. The walk ends if the particle reaches either a neighbor position of the nucleus or when the particle leaves the lattice. So the mass is always smaller than the number of the the points in the grids. So at this point, no cluster is created. So in the next one, we have the same situation. However, we have a neighbor position to the nucleus, so a cluster occurs. So the neighboring position is reached, the cluster is created. So, and then we can start with another particle at the starting point, and so on, and so on. And this is why this can be used to create some fractal geometry. So here an example. This is a glass plate, an architectural glass, and you see here a structure which is very similar to that what we can simulate with this DLA. So here, for example, with a probability of 0.1, we achieved this one, which is, okay, we need some more particles, but it is very close to what we see in real world. So the probability of 0.05 is a little bit denser and more denser than this PO of 0.01. The smaller the probability, the denser the surface. So here some further generation or more fractal geometries at a boundary. So this is chalcedony and some fractal damage in car. So it can be also simulated in a pretty good way. And by the way, also viscous fingering can also be simulated. So the radius of the gyration defines then the damaged area, and with this damaged area you can simplify this model to a 1 minus d damage. You just have to add all the particles that are fractal damage, and then the area or the radius of gyration, this formula, and you can then use it as a 1 minus d damage, which is more practical than this fractal damage, especially for industry, for the industry. So now let's simulate fractal damage using open radius. Here, this is already implemented in open radius, so you can start playing with it. The first one, also here are in total 9 structures, and I'm going to explain it in detail now. Image 2 versus 7. So the starting point, the nucleus, so which is always the yellow point in this image, is in the middle left, and the difference, a very small difference, look a little bit closer to it, occurs, and this is between these two patterns that the model was started twice in a row. So we have always a little change in the simulation. So the next one, image 2 versus 3. So the models are absolutely identical. However, the Z value, this is the value which is a number used to initialize a pseudo-random number generator, has been changed. This gives a slightly different result. So maybe you can see it in at the end of these structures by comparison. Another one, so image 2 versus 1. In image 1, fewer particles just are used, oxygen or hydrogen, than in the second image. And more comparison, image 4 versus 2. So it's nearly the same as in image 2, only the starting point is in the middle at the top. Well, image 5 versus 6, the starting point of the particles is purely random. So the calculation was carried out twice with different seed values for the random number generator. So it's a little bit different, but not very pronounced. So, but by the way, it is very close to this damaged architectural class as shown before. So just the last one, image 8, is the same as in image 2, while the starting point is in the middle at the bottom. Yeah, now finally, the same as in image 2, only the starting point is near the top right corner. So now on practical application, hail impact on a wind screen. So now we study the damage evolution in the event of hail impact of windshield. Step 1, define the weight and size of the hail. So step 2, determine initialization and growth of fracture damage via DLA. And the third step, nonlinear explicit FE simulation using open radius is available. Here are some hails, just for giving a clue for what happens. That's the bigger one. And so numerically, we shot the hail on the wind screen. And here we see nothing. And and this was the undamaged windscreen. And with the damaged windscreen, we do the same thing, and then fracture occurs. So this is the curve, the acceleration curve. You see the upper one here, the green line, which is without damage, and the pink line is with damage. So clearly, in the case of a pedestrian, in the case of pedestrian protection, the pink curve is preferable. So yeah, the damaged windshield is significantly softer than the softer and therefore better in the event of a head impact. And a head impact, this is a head impactor in the automotive industry. So the head is shot with 30 kilometers per hour to the windscreen, and the acceleration is measured. So in Europe, the risk of a hail impact is very, very, very low, but pedestrian protection is more important at this point. So again, some stochastic fracture simulation of glass and transparent polymers. Here, what happens when a car hits a pedestrian? Then, yeah, first contact is the leg, then you wrap around the hood, and independence of size of the person or of the car, the head hits the bonnet or the windscreen. So this is what we see here in this slide. So motivation. So why care about glass and transparent polymers? The problem is if the head hits the windshield, then it automatically is an issue. So side windows, side windows and head impact on side windows, yes, it's possible. For example, a bike cyclist hits the car from the side and the head hits the side window. So in automotive industry, usually glass is used. So, but it can also be a case that acrylic glass, so PMMA, for example, polymetal methacrylate, can be used. It is not so heavy as glass, so you save some weight. So here an example of an impact. No. No. Ah. Yeah. Yeah. Thank you. So. Okay, this is not the one-to-one relation to a full car crash with a pedestrian, but it gives an idea that there are a lot of accelerations for this head. So okay, how to sorry. Yeah, the next step is the head impact on windscreens, and we have here with some windshields HIC 15 values, which varies between 418 and 566 and 10 identical tests, and that brings the idea that statistic becomes an issue. So the initial failure was between 1 and 7 millimeters, and the acceleration is completely different in two different tests, as you can see here, acceleration versus time. So therefore, we measured in an impact head impacts on wind screens with velocities in quasi-static and up to 1 meter per second. 4-point support, so it's not exactly what happens in a car, but 4-point supported allows for a better understanding what happens. So otherwise, if we glue it, then the glue has the adhesive has an influence and so on. So we decided it for this 4-point situation. So here you see the situation. So force over displacement, and the force over displacement curve is very nice, reproducible, but not the fracture. The fracture can be seen here. It goes from nearly 60 to 120 millimeters. So in the next step, we made some ring-on-ring tests. The glass samples were taken out from Audi A3 windshield by water jet cutting, and under different strain rates. So 0.2, 2, and 20 megapascal per second. And this is the result using a 2-parameter Weibull distribution. As you can see here, the higher the stress rate and the higher is the failure stress. So a correlation of stress at failure and initial crack length can be done via fractal mechanics. So we can use these curves, and with these curves we can detect and measure the initial crack length in glass pane. Yeah. So this is the background is still linear elastic fracture mechanics. So implemented is that in open radius, it's fail alta since 2020 already. So, and now let me show you the front windshield and the Higgs distribution, Audi A3 again, glued to a wooden frame to have a situation very close to a real car crash. So this is the simulation, and the normal distribution of 29 simulations can be seen here in this diagram. And a very important thing is the acceleration here, or the Higgs value with this formula shown before, may not reach 1000. Then it is no chance to survive. So on that can you see here in our statistical plot here. So the green area is less than 1000, and the red area is larger than 1000. So that's here in this area we found such an area, and the question is how to deal with it. I don't know. We have to live with such things that are in a very large number of accidents, and will be some people who die. This is the conclusion of this simulation. So here again the side window, and in this side window we use PMMA, so an acrylic glass, and did for this acrylic glass, another stochastic fracture simulation. So the substitution of mineral glass with acrylic glass, weight reduction is always an issue. Unseen free-form designs, and this is also possible, only possible for the side window. So it looks a little bit like this. This was a model for the Mercedes Class M. So here we used some head impact tests and the stochastic simulation. So here is the test. Side window and head impact, for example, by a bicycle or something like that. So here is a brittle acrylic glass. And this is the acceleration. With 150 G, it is not critical. So PMMA can be used for that. Another one, toughened safety glass. This is the usual glass in our cars at side windows. It looks like that. This is the guy on the head guy, the guy's head on a bicycle. It looks a little bit like water, but it is glass. Toughened safety glass. And again, the acceleration is not very high. This guy can survive with a high probability. So now the last one, an impact-resistant acrylic glass. It is impact resistant, right? So, and this is the acceleration. It's death proof. So, finally, some input data for stochastic simulation. We tested over 360 tests, and the test setup is seen here on just a tensile set. So this is the curves for the PMMA, and here we can see the rate dependency of the material. So with ongoing strain rate, the stiffer is the response. So here collected in this probability plot over the fracture strain, and fitted by a 2-parameter Weibull distribution. Give a better idea what happens. So finally, we use the 5 and 95% limit here, and here and solving for the system of equation for beta and eta, and it can be seen here in this one, or in a 3D plot with strain and strain rate, the probability. So this is available in Matt Erosion cards and Alice Steiner, for example. So last, one of the last slides. Here is a simulation mesh size 5 millimeter. Was okay is for an automotive glass. Viscoelastic model for PMMA, and validation of the fracture strain. It can be seen here. and experiment and simulation are very close to each other. And we can calculate the Higgs value from this blue area, and finally the head injury criterion here, the frequency is nearly almost green. However, there is this part here which is red, so we have to live with some final injuries. So, summary. The Higgs values are strongly influenced by the fracture behavior of the material, and stochastic simulation are the basis for reliable design. This is only my opinion. Appropriate material tests must be carried out. It's clear weight-dependent distribution functions are required for input in stochastic simulations. And a stochastic failure model for glass has already been implemented through open radios. So, thank you for your attention.